Okay, so with that, let's jump into our first part of this course, which is the C program to assembly language. Okay, what are we going to do in this course? Basically, in this part, we are going to, this is the, the outline or the agenda. So, I will start with an introduction, right? I'll give you a brief overview of the x86 instruction set, right? We will also get into some assembly programming for the using the x86 instructions. Okay, I'll tell you why we are doing x86 and so on, right? Then I'll jump into compiling and linking a C program, right? I'll tell you what compilation means, what linking means. Then I'll actually jump into the process of taking a C program from scratch and compiling it to its assembly equivalent. In the process, we'll look at, what happens when you pass fewer arguments to a function than what was defined. What happens when you pass more arguments? How do you do parameter pushing? What about memory alignment? And I'll also look at some ideas of exploiting the x86 instruction set. Okay. So the way this course is organized is the x86 is what you called a CISC processor. It's a complex instruction set computer, right? Now this architecture, essentially, as the name suggests, allows for very complex instructions, right? In fact, it can do all sorts of things, right? Now this is very good because it allows us to actually take a C program into its assembly equivalent very easily, right? But it also means that implementing this processor is going to be a little hard, and therefore there is another class of processors called the RISC processor, reduced instruction set computer, right? RISC, RISC, right? Now, therefore, in this course, we will start with CISC. We will understand, okay, what are the kind of instructions, we'll understand the shortcomings, and then we will move to the RISC processor and implement a RISC processor in the second part of the course. Okay, that's the basic idea and the flow of this course. So let's start with the introduction in this part. Okay, so what am I first of all talking about? So I am talking about, okay, a high level language like C. Okay, C, C++, all these languages are high level languages, right? And on the other side, I also have something known as assembly language. What is assembly language? Like I told you, it's actually some human readable machine code. The machine code is what the computer understands. It can decode it and do whatever instruction is needed. But that will also translate 1:1 to some sort of a human readable instruction. Okay, assembly instruction is what we call it. So these are, two quite different languages, programming languages. Okay, for example, if you look at the properties of a high level language, right? Essentially, when you write a C program, you really don't worry about whether the underlying processor is an x86 processor or whether it's an ARM processor or whether it's a RISC processor or whatever it is, right? You just go ahead, write your printfs, for loops, while loops and so on, right? So therefore, it is completely independent of the hardware. Okay. On the other hand, the assembly language, right? What kind of instructions are available for a given microprocessor is very much dependent on the hardware and the kind of implementation, right? Now, what is machine code? Like I told you, it is it's a binary format of an instruction that the computer can easily understand, right? Now, when you write one line of C code, this could potentially translate to many machine instructions, machine codes, right? On the other hand, the assembly language, mostly there is a one-to-one translation. Okay, so if you give me an assembly instruction and I ask you what is the corresponding machine code, it's easy to generate this 1:1. Okay. On the other hand, if you give me a C code and ask me, give me one machine instruction that will do this, it may not be possible, right? Now, the what are the kind of programs that you write in a high level language? You can write very, very complex programs, right? In fact, even in a language like C, right, you are able to write extremely complex programs and and implement such fantastic functionality, right? On the other hand, the assembly language is, you will see later in this course, is quite involved and is quite laborious, and therefore you will not be implementing something very, very complex, okay? In assembly language, you will mostly restrict yourself to writing simple pieces of assembly code. Now, ease of programming, of course, a high level language is much easier to program and to learn than to program something in assembly language. So for the same task, it is obviously easier to write it in something like C program rather than in assembly programs. And how do you achieve programmability, right? Because remember, when you write a C program, you don't write a program to just do 2 plus 2. You write a program to do A plus B, where A and B can be input by the user, and then you return either A plus B, A into B, or whatever, or even way more complex things. What is A and what is B? It's basically what we call variables in C, right? So your programmability comes about because of the use of variables, local variables, global variables, function parameters, and so on. On the other hand, the programmability, right? What is programmability? It is the ability to code and instruct the computer to do something unique, right? And so it's not like a computer is built only to do additions or to do subtractions. It can do any sequence of operations depending on what we tell it, right? And how do we tell it what to do? We tell it through a program. And that's how programmability is achieved. So here the programmability is achieved in assembly language through the concept of registers and memory, which I will be describing in great detail as we go through this course. So given a high level language like this, which has these properties, and an assembly language which basically is way more complex and is hardware dependent and so on, what is it that enables us to do it? It is a compiler. So you take a C code, and if you want to execute it on a RISC processor, then you need to generate instructions for that C code based on a compiler that will give you RISC instructions. Or you want x86 instructions, then you need a compiler that will take the same C code and generate a different set of instructions which are compatible with the x86 processor, right? So now when I talk about this whole thing, right, I spoke about high level languages. Like high level language could even be Python or C++, Java, right? So when I am in this particular course, what is the high level language that I am going to talk about? Why did I pick that, right, amongst these many choices? Likewise, which is the assembly language that I am going to talk about, right? Is it RISC? Is it CISC? Is it x86? I'll tell you how and why we chose that, and which compiler, okay? Because even after I fix, let's say, C programming and x86 instructions, I could have different kinds of compilers that will generate that code. I could have GCC, I could have MSVC, and so on, right? So I need to fix these three. For the purpose of this course, it's only an illustration, that we are fixing these parameters. Technically, the concepts could carry over to whichever high level language or whichever low level language and whatever compiler you use, okay? So which high level language, okay? Which high level language? So what is shown here is basically in mathematics what they call a sequence. So if you look at this, 1, 1.4, 1.41, 1.414, it's a sequence of numbers. Each number is greater than the subsequent number by some amount, right? And if you remember what you did, in earlier in mathematics, you will realize that this sequence actually converges to what is known as root 2, okay? Now the beauty of this is that every term in this sequence, okay, is actually a rational number. By the way, you might be wondering why I'm talking about mathematics all of a sudden, but you will see very soon why I'm actually bringing out this analogy. Every term in this sequence 1.4, 1.41, 1.414, right? Because these are, fixed decimal, fixed digits after a decimal point, they are all rational numbers, right? But root 2 is an irrational number. So this sequence converges to an irrational number, though every term in this sequence is actually a purely rational number. Okay. So, and root 2 is basically the least upper bound of this sequence. Okay. What does least upper bound mean? For example, for this sequence, 1, 1.4, 1.41, 2 is also an upper bound. Okay. You will never hit, none of these terms will actually be equal to 2. Okay. But 2 is still greater than every term. So, it's an upper bound to every term in this sequence, right? But 1.5 is also an upper bound, right? So, as you keep looking at all the upper bounds and take the least amongst them, right? The minimum of those set of upper bounds, that's what we call as the least upper bound of the sequence, and that is what is root 2. Okay. Now, what is the beauty of this root 2? Root 2 is irrational, as I told you, but if I go even epsilon little bit to the left, I will hit a rational number. Okay. So, in my view, if you take all the assembly languages, you take the RISC, which has minimum set of instructions, x86, then you add more instructions to this x86, you add even more instructions to the x86 and order them in increasing order of complexity, right? Every one term, every one assembly language here is going to be an assembly language, right? AL1, AL2, AL3, it's an assembly language. However, I would argue that the least upper bound of all these assembly languages is C. Okay, in some sense, C is so close to the hardware, as you will see in this couple of lectures, right? You will see that C is very, very close to hardware, right? Once you go to Python and C++ and all that, it takes a lot of effort to, take those things and map it to actual hardware or assembly instructions. So, I would argue that the programming language C is the least upper bound of all assembly languages. Anything lesser than C will become an assembly language. So, C provides the kind of functionality that you can achieve with a high level language, okay? But at the same time, it is so close to the hardware and it is so relatable to assembly language, and that is why I argue that C is like root 2. Okay, it's like that. It is not an assembly language, it's a high level language, okay, but it is the least upper bound. To the right of C, you will have C, C++, Java, Python and all that. Way more, you can do more sophisticated things for programming, but they get further and further away from your assembly language and hardware, and that's the reason I am picking C in this particular course for my high level language. So, just an interesting point here, the C programming, right, was first released in 1972. I think it was called some A and B and then it was called C eventually. But you look at the timeline of this programming language, okay. This is basically the modifications and the changes that have happened to C programming since its first release in 1972. So, you see that up to 2024, there have been how many? 1, 2, 3, 4, 5, 6, about 6 or 7 changes in a span of how many decades? We are talking of 40 years, 4 decades, right? For more than 4 decades, you have had just 7 changes, and these 7 changes are not major changes, they are very minor changes. So, the beauty is, in 1972, when the idea of C programming was conceived, right, it was basically Kernighan and Ritchie had simply thought through all sorts of programming, high level programming ideas and had designed it in such a perfect way, right? And I hope we will be able to appreciate this in the through this course at some point. Now, so which processor should I use? Like I told you, there is a reduced instruction set RISC processor. There is a MIPS, which is also a reduced instruction set instruction computer, set computer, x86, x64. There are a lot of them, right? So what we are going to do is to use x86. Okay. Now, why am I choosing x86? Because the x86 allows you to treat variables in C just like it's some other register. Okay, it allows a certain abstraction, and we'll see at a different point why that is the case, right? So the idea is to use x86 as the example to tell you how to translate it, and also that's a CISC processor, right? So we will exploit some of these complex instructions that are available, and then we will discuss the shortcomings and move to the RISC. Okay, that's the idea here. So again, which compiler? I have the C program, and from there I can go through either MSVC or through GCC and eventually hit my x86 assembly code, right? So what am I going to use as the compiler? I am going to use MSVC as my compiler, right? Microsoft Visual C compiler. Why? Because the syntax for inline assembly is the simplest. It's very easy to actually write this. I'll tell you what inline assembly is. In short, inline assembly is you can write a C program, you know, a function or whatever it is, and then you can switch to some, you know, you can switch to assembly language, write something efficiently and then come back to C. Okay, this movement between C to assembly language is what we call inline assembly, right? So the syntax for inline assembly is easiest with respect to MSVC, and that's the reason I will use MSVC as the compiler. So in summary, we are going to start with a C program, compile it with an MSVC compiler and generate x86 instructions, and we want to be able to do this ourselves eventually, right? Of course, we'll use the MSVC compiler to give us the reference output. We will translate something by ourselves and then compare if these two are the same. Okay, that's the idea of the first part of this course. So what are the references and prerequisites for the first part? Of course, the C programming language by Kernighan and Ritchie, that is the Bible of C programming. It's a very small book, and it's a very terse book. Okay, it's a dense, terse book, but it's a beautiful read. Okay, especially if you already know C programming and then you want to understand some concepts better, right? I will also help you sort of appreciate this book a little better through these lectures. And of course, the Intel microprocessor, right, architecture, programming and interfacing by Barry Bray is a very good reference for the x86 instruction set. But I would say it's not necessary that you buy this book for this course. Any reasonable reference on the internet of x86 instruction set should be good enough. Prerequisites is students should be comfortable with C programming. Focus will be on inline assembly. You should only be comfortable with C programming. Assembly language programming I will sort of cover in this course to a reasonable extent, okay, so that you are able to at least program some simple things in assembly language. So I will be covering that. If you already know some assembly language programming, either RISC or whatever it is, great, right? If not, there's nothing to worry about. I will take care of introducing you to assembly language in this particular course. So what are the learning objectives that we are going to cover in part 1? Okay, what are learning objectives? By the way, learning objectives are the things that you should be able to do as a student after you finish this course. So with respect to function calls in C, you always write functions, right? So you should explain how function calls are translated to assembly language, right? You should be able to tell us how parameters are passed to a function, how default values are handled by the compiler, right? Local variables, you should be able to explain what it means to say local variables are stored on stack, right? These are things that people will say quite often, but they don't have a real physical understanding of what happens in a microprocessor. The idea is when you explain and say that a local variable is stored on stack, you are able to visualize what's actually happening in the memory. Okay, that's the idea. You should be able to demonstrate how local variable space is allocated by the compiler, because remember, in C programming, when you are taught local variables, the first thing that you would have been told is you don't have to allocate any memory for this, right? If you remember, if you want to do malloc, right? If you do malloc, it means you are allocating specifically memory for something, and by doing free, you have to free up that memory, otherwise you'll have a memory leak, right? But for local variables, you don't do all that. The compiler takes care of this entire thing for you, okay? But you should be able to demonstrate and explain how the compiler is doing that for you. Then you should be able to explain what it means to say local variables go out of scope after a function call. You would have heard this concept of scope of a local variable. That is when the function exits, that local variable is gone. What does it mean to say the local variable is gone? That's the idea. Then you should be able to explain function context setup and stack cleanup. You should list out the instructions that need to be executed before entering a function and before exiting it. Okay, you should be able to explain various calling conventions for C functions, right? I'll tell you what these calling conventions are in detail later. And some performance improvement, you should, if you have some hardware instructions that can efficiently do some particular operation, you should know how to exploit it to speed up your C function. And the x86 does provide something like that. Then you should be able to explain why recursion is not a great idea for performance, right? So in C programming or Python, somewhere you might have studied the concept of recursion. So recursion is, while it is functionally very, very useful, easy to understand, it's not very efficient, and we'll see why. Okay. So then we will talk about the idea of memory alignment, right? We'll tell you about what memory alignment is, and mainly we'll also tell you why variables are assigned addresses in a certain way by the compiler. What I mean is how local variables are given a certain address, how function parameters are given a certain address, and so on. Then one of the most powerful features of C is actually the idea of printf. Okay, and printf is if you think about it, the fact that it was implemented right away in 1972 is just mind blowing. Okay, because they were able to introduce the idea of a variable argument list function. You don't have to fix the number of arguments a priori. Okay, so you should be able to justify the direction in which parameters should be pushed onto stack. Okay, so it turns out that when you pass a parameter to a function, you end up pushing something onto stack, but you cannot push it in any direction. We'll discuss why that is the case in this course. Then we will also discuss how variable argument list functions are handled, and how we will specifically discuss how printf is implemented and how it works in hardware. Okay, yeah.